happy to be here. Thanks to the organizers for putting up this meeting. It's heartening to see all these new campuses coming up. I hail myself from a place where there are many wonderful new buildings, and what we all seem to miss is a forest-like ambience, which I also hope will soon come up. So today I'm here to present some exciting recent work which was done in collaboration with Jun-Hyun Yo in Korea and Mike Moore from the United Kingdom. So here we studied Heisenberg spin glasses, vector spin glasses in a random magnetic field, and in particular zero temperature metastable minima. So most of my talk is going to concentrate on an infinite range model, which in the Ising context is called the Sherrington-Kirkpatrick model. What I mean by an infinite range model is, in the schematic there is a bunch of points and they're all connected. Everybody is nearest neighbor. Such a model is this infinite range model. And by spin glass, I mean that these various bonds are, some of them are ferromagnetic in nature, and others have antiferromagnetism, tend to be antiferromagnetic in nature. And so we consider vector spins, which are m component classical vectors, and so the model is like here. So we have this factor m which we have pulled out in order to keep these spins of magnitude unity, and so it's helpful to apply a magnetic field which is random in all component directions. So I'll come to this part in the later half of the talk. In the earlier part, I'm going to concentrate on just the zero field model and just very simple protocol which takes us down to these metastable states. So there's also an allied model which I want to discuss, where we have a one-dimensional model where interactions fall off with distance as a power law, as 1 over r to the sigma, and then there is an allied model, if you wish, where one dilutes some of these bonds and says that instead of making everybody everybody interact with everybody else, you say that okay, there is a certain coordination number associated with every site, and so the probability of there being a bond between two sites I and j is what falls off with distance as a power law. So it turns out that you can do better numerics and so on. So I'll only barely discuss one plot from this kind of a model, but most of my work will concentrate on the infinite range model. Okay, so the protocol that we adopt to reach these metastable states is the following. So we are at zero temperature, so it's purely energetics. So you go to one spin and then calculate the local field at that point, and then you simply align the spin to the local field. And then you go to the next spin, align it to the local field, and keep doing it for all the spins in your lattice, and that constitutes one sweep. And then you go back and you repeat the whole procedure, do this over and over again, many sweeps, and so eventually your system will settle down to some metastable state, right? So this is a spin glass, so there are tons and tons of metastable states, and so you start with some other random initial state and then do the whole procedure again, and typically you'll reach some other metastable, and you can cover a whole range of metastable states. And then it's of interest to see the overlap between various minima, and so in particular, it's useful to consider the distribution of these overlaps. So there exists a test for identifying the nature of these the eventual state that you have reached. So if your distribution of overlaps is contains only one delta function, or in some cases you can have two of these kinds of delta peaks, you say that it has reached what is called a trivial state, in the sense that there is this notion of replica symmetry, and that replica symmetry is maintained if your P of Q is of this form. Whereas if you have a continuous part to it, then it indicates that there is a replica symmetry breaking. So now a theorem by Newman and Stein from the 99 says that they consider the Ising version of this problem. So they say that if you start from some random initial state, meaning some infinite temperature state, and then quench down to a low temperature metastable state, like in the type of algorithm that we've used, the final P of Q must necessarily be trivial. So there will be no sign of replica symmetry breaking. So we studied this, a similar thing, but with vector spin classes. So there's also some more history which I want to give you, which is so Parisi later on in 2003 showed that for the Ising case, if you do a quench from infinite temperature, a final state has a certain characteristic energy associated with it, which he computed, which we numerically found out to be this number minus 0.73. And so he did confirm that Newman-Stein theorem does hold, and indeed the overlap distribution is this trivial distribution. Now, old work of Bray and Moore from 81 showed that they studied something called one spin flip stable states, which I will explain in a moment. So they showed that if you consider states below a certain critical energy EC, then the system would be constrained to break replica symmetry. So they argued that if you have one spin flip stable states, and if you are at an energy which is below a certain critical energy, then you must necessarily have a replica symmetry breaking state. And this number they computed to be minus 0.672. So this Parisi number is in fact lower than this, and still it has this trivial overlap distribution. And so it's not really a contradiction because of this key aspect that was included here, which is this one spin flip stable states. So what it means is that if you take these states and if you take any spin in there and then you just flip it, then its energy must necessarily increase. But apparently these states which are reached by these kind of algorithms are giving you more than one spin flip stability, meaning that if you can flip a bunch of spins and still you would necessarily go to a higher energy state. And one example of this is of course the absolute ground state, where you can flip as many spins as you want and you would always get a higher energy. And so apparently these states have something more than one spin flip stability, and they have ground state like character to it. So I will show you in a moment that there are other features also which display these absolute ground state like features. So one quick point to make is indeed from our own study of the Heisenberg spin glass, we do find that there is adherence to the Newman-Stein result, although their work was for the Ising case. So we also find that for the Heisenberg model, P of Q is indeed trivial. So when you consider very large system sizes, there is just a delta peak. So I have flashed just one plot for this diluted model, which is called the Vienna-Bray model, when one has infinite range interactions, but with coordination number just 6. And I have also included a certain field, but I can assure you that we tested it for a variety of fields, and the Sherrington-Kirkpatrick model in zero field, and all this give us just a trivial eventual state in adherence to a generalized version of Newman-Stein theorem. So something remarkable we found from our study is the value of the energy that one gets when one has a Heisenberg model. This is for the Sherrington-Kirkpatrick version of the model. So it goes down, this energy in the thermodynamic limit goes to this value of minus 0.915, which is remarkably close to the critical value of Bray and Moore. So Bray and Moore also managed to find these numbers for XY and Heisenberg spin glasses as well. So while for the Ising spin glass, these numbers were much below these quench energies, apparently it seems like when you have vector spins, this algorithm is actually driving your system down to exactly that energy. So it was something of a puzzle why these completely unrelated ways of getting down to a certain metastable state appear to be giving you the same numbers when you have vector spins. And so people never looked at vector spin glasses from this point of view. That's why it was not noticed in all these years. And since the Ising numbers lay far apart, so it was just Parisi's work is the sole work which looked at these kinds of metastable states. Okay, 2 minutes more. Okay, so I want to quickly show you that. Okay, so there is a long, complicated replica symmetry breaking. There's an analytical calculation what one can do of the Hessian around these metastable states, and one can extract the density of states, and so which involves a certain approximation, which is called annealed approximation. So once again, we find to our surprise that the numerical data actually sit almost right on top of this analytical curve. Why the agreement is so good despite the approximation involved is also something that we don't quite understand, but this is also one of our findings. And so I want to quickly tell you what happens when you turn on a magnetic field. So there is something called the Almeida-Thouless line, which separates this high temperature, high field paramagnetic phase from the spin glass phase. So in our work, we are sitting at this point at t equal to 0, and for Heisenberg spin, there is this critical value of the field, HAT, the random field, which is at 1. So apparently these metastable states are also sensitive to this critical point. And so in fact, so that is another of our findings, is that when you study this density of states of the Hessian, so it turns out that at this field, the critical value of the field HR equal to 1, a certain gap opens up. So you cannot see it very well here, so I have zoomed that part of this curve, and so you see that at exactly HR equal to 1, there is a tiny gap which opens up. And so that is also one of the findings of this work, is that this could be a way to actually identify a critical point in models where one cannot do analytical work. So here also it's possible to extract an analytical expression for spin glass susceptibility. Once again, the numerics, this is the analytical curve, and for large system sizes, indeed, this chi-SD inverse seems to be going to a divergence at this point. So we also computed this for the Vienna-Brahe model. Just I have a couple of slides. So Vienna-Brahe model doesn't seem to show any divergence here, although the ground state of this model also is supposed to be sensitive to an AT field. There is an AT line which apparently is not being spotted for the diluted model. So this is also something that I want to understand whether this works or not in general. Okay, so in conclusion, I want to say that there is these quenches give us energies which are very close to this critical energy associated with replica symmetry breaking features. And so then the study of the complexity of the replica method within an annealed approximation yields analytical expression for both spin glass susceptibility and for density of states. There is a way to access the Almeida-Thouless line critical point, and so below the critical field, annealed approximation is only an approximation, and still the density of states seem to agree excellently with numerical simulations. Why it does so is also something that we want to get an explanation for, and thank you for your attention.
Okay, thanks a lot. Maybe one or two questions. Yeah.
This the gap vanishing at the critical point. So that means this metastable minimas, they kind of get flatter, like less deep. Is that, I mean, as you approach the that's what.
Not sure. I'm not sure. But the Hessian has this feature to it. So I don't know.
So if the eigenvalue is come, there's no gap, then yeah, it is becoming. So, I guess it becomes basically marginally stable.
That's
when,
right.
When the eigenvalue is exactly equal to 0.
But is it something that you would expect exactly precisely at the critical point? Okay. I'm not.
Yeah.
No, density, the Hessian itself contains the fluctuations, right? So it is the fluctuations around the. Right. Okay, so that we have not studied.
Okay, I guess if there are no other questions, then thank the speaker again, and then we'll move on to the